In this video, we will talk about what conditional probability is. So I'm going to motivate this with an example, which says that a jar contains 3 green, 5 blue, and 2 orange marbles. 1 marble is selected at random. Given that this marble is not blue, what is the probability that it is? Part A asks green. Okay, so we want to find the probability that we have a green marble, given that it is not blue. Okay, so in this problem, when we're selecting this marble at random, it's implied that each of these outcomes, like picking any of these greens or blues or orange marbles, that these are all equally likely. Okay, so in total in this problem, if I add up the 3 plus 5 plus 2, there are 10 total marbles. So we have an equally likely chance of picking any of those 10 marbles. Okay, so when we want to find the probability of getting a green one, given that this marble is not blue, we are sort of limiting ourselves to the universe of non-blue marbles. So in the denominator, instead of writing the total number of outcomes, I'm going to write the total number of remaining outcomes. And by remaining outcomes, I mean that we are limiting ourselves to the non-blue marbles. Okay, and on the numerator, we have the number of successful outcomes. So the successful outcomes, and let's specify, well, what does success mean in this context? So in this context, we are after the probability that we get a green one, given that it's not blue. So a success means that we have a green and not blue marble. Not blue marble, but a green marble is definitely not blue. So this is just a green marble here. All right, so let's work out this probability. On the numerator, I just got to count the number of green marbles, and the problem says there's 3. On the denominator, I need the number of non-blue ones. So there's 3 green ones plus 2 orange ones. So we will get 3/5, and that is our probability. So when we have a probability like this, the probability of something given that something else happens, this is called a conditional probability. So called a conditional probability. Because we are given a condition that the marble is not blue. All right, so we have a notation for probabilities like this. So let's state that next. So if we want to find the probability of some event A, given that an event B occurs, we will notate that. We will write that as P parentheses A. I'll write a vertical line to mean given that, and then I write B. And that's going to be our shorthand notation for stuff like this. So let's practice this with another part to this example. Now let's find, given that this marble is not blue, what's the probability that it is orange? So we want to find the probability that the marble is orange, given that, so that's my vertical line, given that it is not blue. So setting up our fraction for probability, on the denominator, I need to count the total number of non-blues, because we're limiting ourselves to the universe, to this condition that our marble is not blue. And on the numerator, we need to count the number of marbles that are not blue that also happen to be orange. So I'm just going to write the number of oranges that are not blue. But all oranges, it turns out, are not blue. So in the numerator, I'm just counting the number of oranges. And the problem told me that, well, there's 2 of them. Right, 2 orange marbles. And how many non-blues are there? Well, we saw there's 5 in part A. So our probability is 2/5. Okay, so the next natural question is, now that we have this feel for what a conditional probability is there a formula for conditional probabilities? And let's try to motivate that with a Venn diagram. So let's consider a Venn diagram of the situation in part A. So I'm going to let capital G be the event that a green marble is selected. And the other event was that a blue is not selected. So let me call that N for not. A blue marble is not selected. So let's draw a Venn diagram. So I'm going to draw some circles. So I'll draw a circle for the event G. And let's draw a circle for the event N. And let's put that all in our rectangle for the universal set, which we can call S here for the sample space, the set of all possible outcomes. So when we write a conditional probability like the probability of G given that N occurs, when we're saying given that N occurs, it means that we are sort of limiting ourselves to all the outcomes within N. So this probability has a sample space that is just N, because we are limiting ourselves to outcomes in N. That is the condition that we are limiting ourselves to. Okay, and in this context, we are trying to find the probability, given that we're in N, that G occurs. So if we're within the N circle, G occurs if we happen to be in this intersection. So we have a success if we are in this intersection. I'm going to shade that in a little bit. So for equally likely outcomes, like we had in this example, equally likely outcomes, when we try to compute this conditional probability, like probability of G given that N occurs, in the denominator, we're limiting ourselves to the condition that N occurs. So we're counting the total number of outcomes in N. And on the numerator, given that we're in that universe of N, we have a success if we happen to be in G as well. So the numerator, we need to count the number of ways to be in G and N. In other words, the number of elements in both G and N. Okay, so I am going to simplify this fraction a little bit so I can get a more general formula. So I'm going to do something maybe that's a little bit non-obvious. I'm going to divide the top and the bottom by something to turn both of them into probabilities. And I can turn them into a probability if I divide both of them by the number of elements in the sample space. So N of S. N of S, the number of elements in the sample space. So when I do that, the numerator is the number of ways to be in G and N. That is N of G intersected with N. And we're dividing that by the number of elements in the sample space. So all over the denominator, total number of outcomes in N, we can write as little n of capital N, using that notation. That also gets divided by N of S. And now that we have these divided by N, the number of elements in the sample space, they are probabilities. In fact, the denominator, number of elements in N, divided by the number of elements in the whole sample space, that's the probability of being in N. Similarly, the numerator is the probability of being in G intersected with N. Okay, so it turns out this formula is going to be the basis for our definition of conditional probability, even when our outcomes are not equally likely. So we are ready for that definition next. So in general, we are going to define the conditional probability of event A given that B occurs. We're going to write that as P of A vertical line for given that B as, so probability of A given that B occurs is going to be equal to, on the denominator, we're limiting ourselves to this condition, the condition that B occurs, and I'll write the probability of being in B. And on the numerator, we'll have the probability of A intersected with B. Because to have a success, given that you're in B, this is saying that we also need to be in A. Okay, so this is the most important formula for this section, our definition of conditional probability. So I'm going to highlight this. But notice that it kind of holds true in that Venn diagram we were drawing before. So going back to this Venn diagram, looking at this conditional probability, the condition is we are given that we're in N. So the denominator has to represent the probability that we're in N. The numerator has to constitute the probability of having success. And the success region we said was this intersection, the probability of G intersected with N. And that's exactly the formula that we wrote down for our definition. All right, so in our first example, 1 part A, I just want to verify that if we use this formula for the conditional probability, so for the probability of given that N occurs, we end up with the same thing that we got just using logic. Okay, so our formula says we should have P of N on the bottom, probability of G intersected with N on the top. Okay, so G intersected with N means that our marble is green and it is not blue, because that's what N was. So the denominator N is not blue. And in this problem, how many marbles are not blue? Well, there's 3 greens and 2 oranges, so there's 5 non-blue ones out of 10 total. So the probability of getting a non-blue one is 5 out of 10. And on the top, we got to find the probability of getting a green marble and a not blue one. But if you're green, you're definitely not blue. So when it says green and not blue, that's the same thing as just saying green. So what's the probability of getting a green marble? Well, there were 3 of those out of 10 total. So 3 out of 10 for that probability. And I could divide 2 fractions. I get 3 over 10. When I divide by a fraction like 5 over 10, it's the same thing as multiplying by the reciprocal. So I flip the fraction, 10 over 5, and I multiply by that. And when I multiply these, I can cancel the 10 on the top with the 1 on the bottom and be left with a 1 in both spots. So 3 times 1 on the top is 3. 1 times 5 on the bottom is 5. That is our conditional probability. And just to check, that is the same thing that we got in part A, where we completely used logic and not our formula for conditional probability that we stated here in this definition. But in later examples, we'll see that there are situations where we definitely need to use this formula. So in terms of our goals for this section, we finished our first goal to define what conditional probability is.